Homework is the fours, and it's all conceptual. There's no math on this section. The next time that we talk, we will talk about implementing the information that we learned today into electron configurations. Today we're just talking about where the electrons are residing, what the things are that they're residing within, etc. So today is kind of a segue into the next time that we discuss or have our next lecture. First thing I want to talk about is probability. Now, back when we talked about Rutherford's atom, and he spoke about electrons going around the nucleus like bees around a hive. And I think I mentioned this in an earlier lecture. And then one of his students, Bohr, came along and said, nah, these electrons are located in a specific location at a specific time. It's a little more organized than bees in a random fashion around a hive. So when we talk about probability, we're talking about where we're likely to find an electron. So if you're a hydrogen atom and we want to find that one electron that hydrogen has, we're not going to look real far away from the nucleus. We're going to look in a specific location if we actually cared about that sort of thing. Some of you might have seen Breaking Bad with Heisenberg. So there's the history behind that. It's called the Heisenberg uncertainty principle, which in reality, this actually deals with there's no way to know exactly the velocity or the location of an electron at the same moment in time. It's just a probability where we're likely to find something. So that's what uncertainty deals with there. An orbital, probably one of the more important things that I want you to know, especially for today, it is this, where is it? It's a region of space around a nucleus where you're likely to find an electron. Okay, so an orbital isn't actually a concrete or a structural thing that you're going to discover. You're not going to find it. So when I show you these orbitals, and there's 4 different types of orbitals that we're going to talk about today, I don't want you freaking out going, how in the world does that actually exist around a nucleus? It doesn't. It's just a region of space where you're likely to find an electron. It's not like this school where this room is a concrete 4 walls, well, more than 4 walls, but has a floor, a ceiling, a door that we can come into. A region of space is just that region of space. So let's just get into the funkiness right now. When we talk about orbitals and energy levels, we already talked about ground state. What does ground state mean again? You better remember ground state. I'll give you the scenario with the machine gun again. Ground state is kind of what we're doing right now. We're nice and calm, cool. We're not excited. Energy is not being absorbed by the atom, so all the electrons are in the lowest energy level possible. Or, better stated, they're closest to the nucleus right now. Okay? And, again, what is an orbital? It's a region of space where you're likely to find an electron. And we'll talk about how we're going to divide these things up, or these regions up. Okay? So, let's see. That's all great. Oh, here we go. So let's talk about energy levels. And the next time that we talk, we'll talk about the periodic table in the terms of the energy levels. But what I want you to know right now is, looking at these energy levels, we say that N represents an energy level. And we'll always start with the first energy level. Okay? So if we start with the first energy level, and the next time that we talk, we'll talk about it. It's the very top of the periodic table. In each of these energy levels, there's an equation called N squared. So N squared represents the maximum number of orbitals that can exist in an energy level. So in this case here, if I square 1, what's that value? 1. So in the first energy level, the maximum number of electrons that I can have is 1. In the second energy level, if I do 2 squared, that equals 4. And so on and so forth. So if I had 3 squared, that's 9, 4 is 16, 5 is 25, etc., etc. Okay? So that's what that represents, if you see N squared. Okay? In each orbital, there is a maximum number of electrons. The maximum number of electrons is 2 per orbital. I'm trying to find out where I have that written, but I don't think I I see it anywhere. So the maximum number of electrons per orbital equals 2. Okay? So no more than 2 orbitals per, no more than 2 electrons per orbital. I don't care how complex it is or how simple it is. All right? So knowing that we can only have a maximum number of 2 electrons per orbital, then our equation now changes to this, 2n squared, where the n still represents the energy level. The square means that's the maximum number of orbitals per energy level, but the 2 here represents that now we can have 2 electrons. So in the first energy level, what's the maximum number of electrons? Here, I'll give you a hint. So if I do 2, 1 squared equals 2. Good. Now, if you look at the periodic table, and again, looking at the periodic table, how many elements do we have in the first row? 2. And you're going to find out the next time we talk that that represents the first energy level. Each element's going to represent an electron, so that's why there's only 2 elements up there. Okay? That's just a little taste of what you're going to have next time. And so if we look at, say, the second energy level, what's the total or the maximum number of electrons there? 8. And in the second row on the periodic table, you'll notice that there's 8 elements. And then the third energy level, what's the maximum number? 18. I'll show you where the 18 come at next time we meet. Okay, so that's that equation there. Okay. All right. Oops, sorry. Funky on me here. All right, so let's talk about these orbitals. And we're going to go from the simplest to the more complex. And I think you have these images in your notes as well. So the first orbital that we'll start off with every energy level, whether it's the first or the 7th, we're going to start off with an s orbital. Now, I'm not sure if it's called an s orbital because it is a sphere or if it's simple. I really don't know. Really don't care. But know that it's a sphere. Now, what's the maximum number of electrons that can go in that one orbital? 2. Very good. So no more than 2 electrons in that one s orbital. And the next time that we talk, that will have more significance. Now, I put 2 images on there just to show you what different artists look at that as. Now, notice that it has the x, y, and z coordinates on there. There really isn't an orientation for an s since it's a ball or a sphere, and so it just changes as the orientation moves there. Looking at the next energy level, if we said that we wanted to know how many different orbitals we could have in the second energy level, 2 squared is what? 4. So in this case, we always start every energy level off with an s orbital, and then so we have 1 orbital there, and then we've got these 3 p orbitals. Now the p orbitals kind of look like dumbbells, or whatever your imagination wants to go. Okay. But notice that now we do have these p orbitals actually lying in a particular orientation. So these are actually on the x-axis, that's on the y-axis, and these are on the z-axis. If I take all 3 of those and put them together, I'm actually forming what's called a bumpy ball. So it's kind of starting to change a little bit. And if you think about cell division, we started with a very simple shape, and we split it in half, and now we've got 3 different orbitals here. Okay. How many different electrons can go in this thing that has the 2 bumps on it, so to speak, is considered a single orbital. What I don't want you saying is, well, there's 1 orbital there, and there's another orbital there. No. Collectively, that is a single p orbital. Okay. Okay. And then it gets even more interesting. Okay. Looking at the D's, which are the next option. Notice how it gets even more complex. And again, the orientations are becoming more interesting, but we don't care about the orientation. We just want to know that if I take all 5 of these and put them together, what am I going to make? A bumpy ball. But it's going to have more bumps because we actually have more quote-unquote nodules, so to speak. Okay. And then the last set of orbitals get really crazy looking. They look like this. Okay. Now, here's what I don't want you to do is freak out and go, whoa, what in the world's happening here? Keep in mind that when we look at a nucleus, okay, that dot that I just put on there, that is not to scale. Okay. So if I have an s orbital, and then I have a p orbital, and then I start doing my d orbitals, and then my f orbitals, okay, they get farther and farther away because they're getting more and more complex here. The thing I want to ask, if I look at, say, this one f orbital right here, how many electrons can occupy that one f orbital? What's the maximum number? 2. Very good. So what I don't want you to do is look at this shape and say to yourself, whoa, I can put 2 electrons in each one of those little nodules. No, you can't. That one thing is just simply, if I can locate it again, this is just simply a region of space where you're likely to find an electron, or in this case, 2 electrons. So don't freak out and go, wow, that thing is really complex looking. Yeah, it is. Are you going to have to memorize what that looks like? No. Okay. The shapes that you're going to have to memorize are s orbitals and p orbitals. Okay. So the shapes that you'll have to memorize, there's the p's, there's the s. Think you got it? Okay. What I want you to know is that as we move along, they get more complex. And that makes sense because they're getting farther and farther away. All right. Here's the fun stuff. Okay. If I'm an electron, okay, let's say I'm an electron, and I'm encountering an atom. Okay. Atoms are going to place electrons in the lowest energy levels first before it occupies higher energy levels. So when I look at the s orbitals, the p orbitals, the d orbitals, and the f orbitals, the s orbitals have the lowest energy because it's closest to the nucleus. The f orbitals have the highest energy because it's farthest away from the nucleus. So if I'm an electron, exactly this guy. Oops, sorry. Oh wait, whatever that was. Ooh. Undo. Sorry, I don't know what just happened there. Okay. If I look at these and I'm an electron and I'm moving, say I'm moving through space because some metal just gave me away. And say if I go to the f orbital first and I'm like, ooh, the d is open. There's no electrons in d. It'll move to the d. And if it says, ooh, there's none in the p, it'll move to the p. If there are no electrons in the s, it'll move into the s. The most important thing I want you to get out of that is electrons will fill up the lower orbitals first before it tries to place itself into a higher energy level. Okay? We always occupy, and this will make more sense the next time we talk when we do configurations. So that's what this is saying here. The electron will first occupy or fill the lowest energy orbitals first before it goes to a higher one. So it won't move around out here. It'll occupy here. If that's full, then it's only option P. P's are full, then we have to go to D. If all the D's are full, then we have to put it in the F. Okay? All right. Quantum numbers. When we talk about quantum numbers, it's like an address. Okay? So an electron, we can find an electron, quote unquote, theoretically, based on 4 different variables. Okay? The first one, the letter N, represents the size of the orbital. Okay? In other words, when we look at, say, a 1s orbital, it might be that big. If I look at a 2s orbital, it might be that big. If I look at a 3s orbital, it might be that big. And so on and so forth. So as I increase the energy levels, those orbitals get bigger and bigger. Okay? So 1s, 2s, 3s, 4s, etc. Because when you have an orbital that's filled up, it takes up that space. So we're not going to like cram all those into one singular location. Okay? So the first principal quantum number deals with the size, or the energy level, which I may talk about the next time we speak. The second principal quantum number deals with the shape. So again, our shapes that we care about are S, P, D, and F. Okay? Those are the only shapes that we care about. And then the third one deals with orientation. So orientation, whether you're on the x-axis, the y-axis, the z-axis, whatever, okay, the orientation is different. And then the last one deals with spin. And I have 2 electrons here. So here are 2 electrons. And if you think about an electron, what is the charge on an electron? Negative. So if any of you have ever taken physics and talked about torque, anybody talk about torque? You might take your right hand and curl your fingers in so that when you turn your hand this way, that's the direction of torque. Okay? So whenever you screw in a screw, you always go lefty-tighty, righty-loosey. Is that right? Uh-huh. Nobody's listening. Good night. Righty-tighty, lefty-loosey. So in other words, it's like turn to the right, that's the force of the torque. Okay. So if I had 2 right hands and I'm turning this way, then my torque is going this way, quote unquote. However, since an electron is negative and it is spinning, okay, if it starts spinning, it generates a magnetic field. So really I have 2 electrons here because as they're spinning, they're oppositely spinning and they're causing different magnetic fields to take place. If I had 2 electrons with the same spin, what do you think is going to happen to one of those electrons? It's going to kick it out. Okay? But if they're opposite spins, then they'll stay together. Okay? So same spin, kicks it out, opposite, stay together. Now, that's the thing with the spin, and that's why we can only have 2 electrons, because as one's spinning, it generates a certain magnetic field, whether north, up, south, down, and vice versa for the other one. Okay? So those are our 4 principal quantum numbers. If I were to say, okay, I have, say, an s orbital that, let's say it's in the first energy level with an s orbital, and I decide to put it in the x-axis. Okay? Can I have another electron? And let me also put it with a 1/2 spin. Can I have another electron that's in the first energy level in the s orbital along the x-axis with a +1/2 spin? No. Why? Very good. One of those will be kicked out. Let me ask you this. What if I had 2 orbitals? Okay. Let's say that I had, let's not do that, but let's say that I had, say in the third energy level, I have a d orbital and it's along the x-axis. Okay. Can I have 2 of those orbitals in the same exact location? Okay, pretend that I'm a twin. Okay, I have a twin, and he's standing right there. Okay, we're both the same size. If I'm standing here, can my twin occupy the same space that I'm occupying? No. So those first 3 quantum numbers can't be the same. In other words, I can't have an x-axis. It might be along the y-axis. Okay. So when we talk about orientation, when you look at those pictures, they're kind of adjusted a little bit. And that was one thing that somebody last period noticed and said, do we have to memorize those? Oh, no. You don't ever have to memorize those orientations. Let me get it. So like if I look at these shapes on the bottom here, they're kind of different a little bit. And if I take all those and put them together, it kind of forms a bumpy ball. So there's no way that whatever this orientation is, it says X, Y, Z, and then don't worry about those math functions down there. But I cannot have 2 f orbitals that look exactly like this in the same location. That cannot happen because it's occupying the same space. Does that make sense? I hope so. All right, and here is a nice little table that helps to summarize everything that we've talked about today. Now, the good news is, yeah, you're going to need to know this for the test, but after the next lecture, the periodic table will actually show this for you. You just don't realize that the periodic table that we have gives us all this information. All right, the homework for today is the 4s, so go ahead and work on that. That'll be due at the beginning of the period next time that we meet.